Can you hear me now? Great. Yeah, thank you. I will start this talk by motivating using neural networks for solving PDEs and stating the principle. And then I'll go through two examples. And then finally, I'll focus on the pain points of this method. And that's going to bring us to how solving PDEs with neural networks differs from machine learning. So astrophysical PDEs, for example, one example is magnetized gas flow combined with viscous or diffusive transport combined with classical gravitation. That's the type of PDE that we encounter in the studies of star formation. If you try to solve it, you realize that, well, the methods are all based on spatiotemporal discretization, and they are distillations of decades of numerical experimentation and are problem-specific, elaborate, and contrived. For example, we just heard about finite volume methods involving polynomial reconstruction, slope limiters, upwinding, approximate Riemann solvers, implicit and multi-grid methods, etc. Those of you who have taken this piece of light reading to the beach, you know what I'm talking about. Now, the prototyping of solutions to new problems that have not benefited from this type of legacy of decades of trial and error is difficult, especially to beginners. Now, there is a slightly different approach to attacking PDEs with PDEs, which involves considering a function space that's discretized in some particular way, and then attempting to directly minimize the degree to which functional representations violate the PDE. For example, in the so-called least squares finite element methods, we are minimizing the square of the residual that should be 0 if the PDE is to be satisfied. Okay, so this least squares finite element method, this is sort of older method, directly plugs into using neural networks for functional representation. So we approximate candidate solutions with a neural network. Here, this f of x is x is the, for example, space-time coordinate, that's the input to a neural network, and theta summarizes all the parameters of a neural network, the weights and the biases. You can have millions of them. And then the partial differential equation can be written as, okay, some nonlinear differential operator d acting on an f should be 0 in a spatial temporal domain. And also, the network should satisfy some boundary conditions. So it should equal to some, for example, boundary data g. The advantage of neural networks is that this nonlinear differential operator can be executed symbolically with frameworks like TensorFlow and PyTorch. So we would like to, we solve the PDE by minimizing the residual and the boundary violation. That is, we have a loss function that has two terms. The residual violation integrated over the entire spatial temporal domain, and the boundary violation, where we could be using the square norm or an L1 norm or any other choice. And now, okay, so I'm not going to explain neural networks in detail, but okay, what's important here is that with smooth activation and nonlinearities, the approximations are smooth and infinitely differentiable. The PDE residual minimization is formulated just like empirical risk minimization in deep machine learning. The prototypical model is if you think about a model building, is a nonlinear differential operator head on top of a standard multi-layer persistron backbone. Neural networks of increasing width are universal functional approximators. We know that, that there is a parameter vector that solves the PDE, but can we find these solutions? That's the central question. And let me just mention that this idea was proposed more than 20 years ago, but then there's been a recent resurgence of interest. And I'm just listing some representative references. Ours just came out on arXiv. A little while ago. Okay, here is my first example. is the one-dimensional Euler shock tube. So what you have is a pipe containing gas. There is a barrier. The pressure on the left and right of the barrier and the density on the left and right are different. If you yank the barrier very quickly, you'll have a pressure imbalance, and that is going to drive the fluid, the gas, to move. The initial conditions are discontinuous, and that's going to result, and this is sort of textbook introductory gas dynamics, in sort of the rarefaction wave, contact discontinuity, and shock wave that are propagating in space. So what we are doing here is we are solving these equations here. These are the Navier-Stokes equations, so we vary the small viscosity to the Euler system, and comparing with the classical finite volume and discontinuous Galerki methods. And we find that the solution obtained by the neural network is very competitive with those methods. Now, what do we, apples to oranges? No, actually here we're comparing solutions that have the equal number of parameters, which in this case would be the degrees of freedom that can be adjusted. Now, neural solutions are different from classical methods in that you're not advancing in time. You're solving globally in space-time. So that very same problem, now this is the time coordinate. You can see those features travel in time. What you're doing is you're generating random samples of points in the entire space-time, and there you're minimizing the violation of the PD and the boundary conditions for each of these mini-batch. Because every mini-batch is generated randomly, you're basically working with an infinite training set. Therefore, overfitting is not an issue. So now, different view of scaling. Just like we heard in the preceding talk, this method is solving PDEs from scratch is not competitive with finite volume methods, but there are great advantages. Arbitrary boundary experimental data can be incorporated straightforwardly, including big data in the objective. Scaling is under increase of dimensionality is excellent on Harvard accelerators. Adaptation of solutions to modified parameters or boundary data requires retraining from a checkpoint. So you change your parameters, you change anything, you don't have to solve from scratch. And finally, parameters are treated as network inputs. So for example, here there was a parameter gamma, which is the so-called adiabatic index. Let's say that I'm in the business of solving this equation for different values of gamma. All that I have to do is treat gamma as a network input, and then I have a solution that is global, not only in space and time, but in the space of gamma. And that comes out straightforward. You can see how the shock wave location depends on the location of gamma. Here is my second example. This is a little bit more complicated. 3 plus 1 dimensional, 3 space, 1 time, Navier-Stokes equation coupled to classical gravitation. So what I'm doing is I'm colliding two blobs that are self-gravitating. This shows the velocity, so they are moving toward each other. Just to show you how this is in practice, I'm going to now show you the TensorFlow code that where these equations are written. In fact, all the physics here is in this box, where the equations are written now just like you see them in LaTeX. And we're just telling TensorFlow, OK, make all of these things vanish as much as possible. And so here are the results. Here we see this is space-time. We see the two blobs are running into each other. So they're approaching, they collide. Some things look good. So for example, where they collide, the pressure is going to jump, compression. Also, the temperature increases, heating. Entropy jumps as well, which means that entropy is being generated in shocks. Entropy jumps, but then does not quite stay constant. So it's already you see it slightly violates the laws of thermodynamics. And then here I'm plotting the velocity in the vertical direction at the initial conditions. So what the neural network is doing, not only solving the PDEs, is fitting the initial conditions that are provided. And you see that there's actually the neural network insinuated artificial vertical spreading of this blob. And that wasn't there in the initial conditions. So you can see that neural network is actually it is modifying the problem so that to make it easier to solve. In other words, if you add a vertical velocity, density is going to drop. The flow is going to be simpler. So that's of course not good. And so let me then get into some philosophy here. Whereas machine learning is about generalization. Okay, in statistical learning, generalization relies on the smoothness of neural functional approximations. All complexity, and that means variation in the data, is explicit in a supervisory signal. So now, over a parameterized neural network, generalized well, we all know that, it's an amazing feature. Outside of the finite training samples, because stochastic gradient descent find these smooth approximations which correspond to wide or locally flat minima in the loss landscape. And in fact, stochastic gradient descent behaves like a dynamical system at a finite temperature, where temperature is the learning rate divided by the batch size. Now, solving PDEs is actually about finding sharp minima. And so here, this is the Burger's equation we heard about. So let's say you start with a sine wave, and in time, this sine wave evolves nonlinearly to break. So the initial data have low complexity, low spatial frequencies, but with time, high spatial frequencies develop, and in fact, here they blow up. So the complexity of the solution is not explicit in the initial conditions. It is implicit in the equations. And in fact, in order for the solution to fit this breaking of the Burger's wave, the global minimizer of the PDE is going to be is going to correspond to a narrow or sharp minimum in the loss landscape. And it's not the kind of minimum that will generalize in machine learning, and is not the kind of minimum that SGD can easily find. In fact, stochastic gradient descent family methods can be dynamically unstable in the minima that solve hard PDEs. And so if you want to see this thing, I'm sorry, this is crowded. But for example, consider this arctangent function, and it's arctangent on alpha x. And let's say you can write down an ODE that does not depend on alpha, actually it's over there, that has a solution, an arctangent of alpha x for arbitrary alpha. And then your boundary conditions are how close it is to the minus pi over 2 and pi over 2 at the two ends. So it's really through the boundary condition that you make closer to the to minus pi over 2 and pi over 2. You're making the solution in the middle is going to be steeper and steeper, right? So small boundary, very small value there is going to imply larger steepness here, but that steepness is not explicit in the inputs. And so imagine the loss landscape as follows. So this is the objective function, the square of the PDE residual plus the square of the violation of the boundary conditions. You will have one direction along which the boundary condition is satisfied better. It's this arrow here. And then at any given point, we'll also have a high curvature direction in which the PDE is violated. So when we don't satisfy the boundary condition very well, it's easy to satisfy the PDE because the curvature is low. But as we start satisfying the boundary condition better and better, the curvature gets larger and larger, and it's much harder for stochastic gradient descent family methods to settle in this minimum here. So now if you're running stochastic gradient descent at low temperature, which means small learning rate or large batch size, it will get stuck in these local minima. If you're running it at high temperature, it will not be able to, it will be dynamically unstable where you want it to be. So, so here is the outlook. Okay, so the possibilities are endless. I'm fantasizing, I like to fantasize. Okay, so let's use this method to solve the Vlasov kinetics, like plasma dynamics or gravitational dynamics. What about neural general relativity? What about neural turbulence? And there are actually very active research areas right now. The first, Professor Kutz's talk this morning, neural inverse problems and neural physics discovery and system identification, very much in line with the method that I described. And I'd like to leave you with the conclusion that optimization is the principal challenge. in this method. Thank you.